Okay, let us continue our lectures devoted to the properties of characteristic functional of the probability distribution in the Banach space. So the main object which we consider is the following. We consider Banach space B with the Borel sigma field. We consider mu probability distribution. Probability distribution on B. We consider the following functional phi mu of f, which is equal to the integral with respect to b exponent e f of u mu du, where f is an element of the conjugated space B star. And we discussed last time that this characteristic functional of the measure mu has the properties which are very similar to the case when B is finite dimensional Euclid space. Namely, it is non-negative definite, it is equicontinuous, it is symmetric, and it has, in sense of complex numbers, and it has value 1 at the point f equal to 0. But after this, we have seen that a lot of good ideas finite. For example, we know that in finite dimensional case, the properties which I already mentioned are enough for the function to be a characteristic functional of some probability distribution. But it occurs that in infinite dimensional case, it is not true. And in order to understand what happened and what we need to add to the requirements of the characteristic of the functions in order it to be characteristic functional, or in order to understand what properties have characteristic functionals, we started from the simple but very interesting and very important case when instead of the Banach space B, we considered Hilbert separable space H. So we consider H is a real separable Hilbert space. And we considered measure mu, or equivalently, it is the same Gaussian random element. Xi is a Gaussian random element in H. Mu is its distribution, so it is. And we discussed what are the properties of the main operators related to the Gaussian distribution, because we remember that in the finite dimensional case, Gaussian vector was characterized completely by the two subjects, mean, and another one it's covariance matrix. And it occurs that the characteristic function of the Gaussian random vector was easily written in the sense of mean and covariance. So we expect that more or less the same must happen here, but when we began to discuss mean and covariance, we invented new interesting features. Let me recall you what we did last time. As it follows from the definition, for all u which belongs to our space H, this scalar product u psi is a Gaussian random space. Due to this definition, we were able to define the linear operator which is acting from the space H by the following rule. In the space of a square degree random variable defined on our probability space. And it occurs that this operator is continuous. Due to the closed graph theorem. And due to the closed graph theorem. We to discuss the following. For example, we can apply now continuous linear functional from this space to R, like expectation, and then we get such a line. We start from U, from the space H, then we make it into U psi, and this is continuous method. We already did this. Then we map it to expectation of U psi, and it is also continuous method. Yes. So the superposition is also continuous, and now we understand. And the usual representation for continuous linear functionals, like the some element of our space H M, and we said that M is a mean of psi, and then we considered centered case. So we supposed that M is equal to 0. From now, M is equal to 0. Simply one can consider new random vector psi equal psi minus 0. And then we began to discuss covariance. In this case, where we have centered vector, we just considered operator Q, U, V, which has this linear form, which is defined like expectation of u psi or v psi, and we discussed this linear form is continuous. Due to this fact, we can say that it is generated by the continuous linear self-adjoint positive operator. So we know that Q is continuous. Q is self-adjoint because of we can interchange the multipliers, and Q is non-negative in the operator sense. So we have such kind of operators, and then we study it more carefully. Because up to this moment, it is natural and it is expected from the finite dimensional case. Because in finite dimensional case, as we remember, a covariance matrix can be treated as a continuous operator in our finite dimensional Euclid space. So one can say, okay, nothing new. We just have again continuous self-adjoint and non-negative analog of matrix, and that's all. But this is only the beginning of the story, because last time we invented that Q is compact. So last time, our last statement on the lecture was the following. We proved that Q is compact. After this, we immediately can apply this representation theorem for compact operator. Moreover, it is self-adjoint and non-negative. So, from the Riesz representation theorem for compact operators, we get that Q uniquely has the following representation. Q is equal to the sum from K equal 1 to infinity, lambda K. Here is EK. I use here the symbol of the tensor product, but I will explain what is it, and we don't need all theory of tensor products now. So now here EK is greater or equal than 1 is also normal basis in H. Lambda K are non-negative numbers. I will suppose that some of them can be equal 0 in order to say that this is basis. Yes, because sometimes we want to have, for example, finite dimensional operator. It can be, but in those cases, lambda from some number are equal to 0. Yeah. So we just have such a representation, and Okay, let's continue. So our operators ek to the multiply ek are just one-dimensional operators which are acting as it is written. Our operator Q, and we will have a lot of interesting consequences from this representation. Why? Let me recall you definition of Q. We define this operator Q using bilinear form and define it by expectation of linear functionals related to our Gaussian vector. Q U V was equal to expectation of U psi and V psi. And now let us recall the definition of our random vector, Gaussian random element, and use this representation. Due to orthogonality of ek, we have the following. Now the sequence ek psi, k is greater or equal than 1, k is greater or equal than 1, is Gaussian sequence, yes, because of the definition of our Gaussian random element. So these are jointly Gaussian random values. And they are centered because psi is centered. And they are non-correlated because of this definition and orthogonality of ek. So this is IID sequence of standard normal variables. Here is the following. Here is the following conclusion, which is very interesting because now we understand that excuse me, not standard, but here must be excuse me, this I am too fast, is independent, so this is independent Gaussian lambda k, of course, because of the lambda k. We will do this in the ID sequence, but right now, due to the definition of Q, we have here lambda case. Okay, so now we know that our element psi in the basis ek has the following representation. Psi is equal to the sum from k equal 1 to infinity. This ek psi multiply on ek. Yes. And we know that psi is a Gaussian random element. So we know that sum from k equal 1 to ek psi square by the parseline identity is equal to the norm of psi square and is less than infinity average. So we have the following relation. Now let us analyze it, because here we have an interesting problem related to the convergence of the series of independent random variables. You see, they are independent because they are non-correlated Gaussian, and we know the distribution of these coordinates. It is the following. We will make an interesting conclusion from these two steps. It can be done in different ways, but it seems that one of the simplest is the following. Let us consider the random variable E minus norm psi. Due to this relation, we have that this random variable is almost positive. So the expectation is greater than 0. Yeah. Moreover, due to this representation, it is the limit, and n tends to infinity, of the expectation E minus sum from k equal 1 to n ek psi. Yes, and now due to the independency of this random variables, I can write this expectation as a product, and it is the limit, and n tends to infinity, product from k equal 1 to n. Here is expectation. Here is expectation. Here is E minus ek psi squared. And we know already what is this, because it is simply square of the Gaussian random variable which has known variance 0 mean and known variance lambda k, and it can be easily calculated. Please do it by yourself. That the last line can be written as follows. Oh, we have here a limit, and n tends to infinity, and here is the product. Excuse me, the product from k equal 1 to n, 1 over square root of 1 plus 2 lambda k. That's all. Okay. So what we have that this limit exists and is greater than 0. It means that the following product, the following infinite product of what we have c in the denominator under the square root from k to infinity 1 plus 2 lambda k conversion hence
This should be in some power, yes? 1 plus 2 lambda k should be in power minus 1/2.
I said that if we have here limit of such then we can put square root outside and we can say that
Okay.
we have,
Okay, sorry.
So we have here the following consequence, and now we can use the statement from the analysis, the first year analysis, that when we have the infinite product where the add to 1 is have the same sign, lambda k are non-negative, then it converges if and only if the series from k equal 1 to infinity, lambda k is finite. This is a very interesting conclusion which we get. So we get this conclusion using the expectation of the exponent of the minus norm square of psi. It can be done in various way, as I said. For example, one can apply Kolmogorov theorem about three series and so on. Everything works now, but this way seems to be natural, and we get and we finally get such conclusion. Now let us see what we have. Now let us see what we have. To emphasize the lambda k organized convergent series, now I will use the following notation. I will denote the coordinates of our xi in a special way. It will be square root of lambda k multiplied by psi k. Let us introduce such random variables lambda. Then now I can say the sequence psi case is IID sequence of standard Gaussian variables. So what we have? Let us back to coordinate representation of the random element psi. Now we have the following. Psi is the sum from k equal 1 to infinity square root of lambda k psi k e k, where psi k are independent standard normal variables, ek is orthonormal basis, and non-negative values lambda k are such that the series lambda k is finite. So we have such a representation for arbitrary centered Gaussian random element in the Hilbert space. Sometimes such representation is called Karunen-Loev representation. And it can be generalized not only for Gaussian, but for separable Banach space too. For us, it is interesting now that we have independency, we have such a good property for lambda case, and from now we can make some conclusion. For example, now one can calculate the expectation of the norm of psi square. What is it? What is it? It is equal to expectation of the sum from k equal 1 lambda k psi k square, and it is equal to the sum from k equal 1 to infinity lambda k, and it is less than infinity. It looks like we get that Gaussian random element in infinitely dimensional Hilbert space has second finite moment of the norm. Moreover, using this condition on lambda k in this representation, one can easily check that Gaussian random element has exponential moments of the norm in the Hilbert space. Please check it. So we see that it is that surprisingly we can make a lot of conclusion about the norm of Gaussian random elements just using the initial definition, where we have no any assumptions about infinite dimensional nature of our random element. We just say the element is Gaussian if any scalar product is Gaussian. That's all. But you see how strong conclusion we can get. So one can see from here that our operator Q is the following. Q, let me recall, is self-adjoint. Q is non-negative. And now we know the trace of Q so it is not only compact, it is nuclear trace. Q is nuclear. Now we can finish our investigation of the mean and covariance of Gaussian random vector random element as follows. One can say that any Gaussian random element in Hilbert space is in distribution uniquely defined by two subjects. One is element of Hilbert space, its mean, and another one, Q, is nuclear operator, which is its covariance. So we see how strong is definition of Gaussianity. We for sure get the nuclear operator as covariance operator of Gaussian random vector. Before go further, let us check some examples. Yeah? And it seems to me that good example can be a Wiener process, which we can consider as a random element in the space A2. So I will discuss space A2 0 pi L2 0 pi is a space where we will have our Gaussian random element, space H. Our Gaussian random element will be following. It will be WT, T belongs to interval 0. It is a random element here. Why? Because we know that W has continuous modification, so we can consider it now. W is continuous, and then one can understand that any such integral ut dt where u belongs to this space, u belongs to L2 0 pi.
So integral is also till pi.
Integral, oh yes, thank you very much. This is a standard thinking. When I'm thinking about interval, always you mention just 0, 1. Yeah? Okay, so such integral is also a random variable because it can be constructed by approximation of ut by good functions, and then everything will converge. Yeah? So this is a random variable. Due to this fact, W is a random variable. Due to this fact, W is a random element. In the space. And of course, it is easy to see that this random variable has a limit of simple sums is a Gaussian variable. So W is a Gaussian random element in our space L2. So it must have these two subjects, mean and covariance. Yeah, and we can find this subject now. It's easy. For example, one can consider expectation of the integral from 0 to pi Wt ut dt and we know that this expectation is continuous linear functional. For continuous functions, at least I can take expectation there, and it is equal to 0. Yeah, so it is equal to 0 for all functions for u from here, and from this we understand that the mean of our random element is 0. Here 0 is an element of H. But it is expected. Yes, we already expect that because W is centered random process. Now let us check the covariance. Exactly in the same way, we can put expectation inside of the integral, which represent for us scalar product, and one can get the covariance operator has the following bilinear form. QUV must be equal the integral from 0 to pi T minima S ut Vs dt ds. This is just a representation which is expected. From this representation, we can take a lot of interesting things. For example, let us recall that when we have Q integral operator with the symmetric, non-negative, definite, and continuous kernel, then its trace is simply integral with respect to diagonal. Yeah? And one can see that yes, we have the nuclear operator now, as we proved already, and we know that trace Q, which is equal to the integral expectation of the integral from 0 to pi wt squared d, is equal to the integral with respect to the diagonal d dt. This is node. And the next one is related to the Caronin-Wall representation for our random element W. What we said, we already checked that now this operator Q must have the system of the eigenvalues related to the eigenbasis Ek in such a way that W can be represented as a sum from k equal 1 to infinity. Here we have square root of lambda k multiplied by psi k and Ek, where psi k is So what we have? We have the following good representation for Wiener process. Maybe some of you know that when we discuss existence of the Wiener process as a mathematical model of the Brownian motion, we formulate usually a list of properties which we need, like continuity, stationary and independency of increments. And then we say, okay, such process exists. And what is the reason? There are different ways. One can say, okay, if it exists, then its values must be Gaussian, because due to the central limit theorem applied to the sum of then we say that due to Kolmogorov theorem, this process exists, it has continuous modification. Another way can be following. Lviv proposed, for example, construction of the Wiener process as a special sum where we get a polygonal approximation of W already inside of the space of continuous functions. Here you see maybe we have another way. Yes, because all what we need to define this and this. Then we can say, okay, this series represents W at least in sense of conversions in square meter. And it is interesting to check what is this. As we said, Q define these sequences. These are eigenvalues. These are excuse me. These are eigenvalues. These are eigenvectors. So we have the following relationship. We have the following relationship that for any k which is greater than or equal to 0, we have ek of t. Let me recall you this is a function is equal to okay lambda k equal to t is equal to integral from 0 to pi let us continue write this integral, splitting it into parts. One is up to the moment t, another one after the moment t. So what we have here the t multiply on the integral from 0 to t, and here is s ek s ds, then plus integral from t to pi. Oh, excuse me, exactly in opposite case. So here s is smaller, so we don't need here t, but here we have t to pi, and here we have ek s ds. Okay. Now I'm for a moment, because we are just thinking how to find this ek. For a moment, suppose that they are continuous and differential. Yeah? Then one can differentiate this equality with respect to t. Yeah? And we will get the following. We'll get the following. Here is lambda k ek prime t is equal to, here is t ek t, here is plus integral from t to pi ek s ds minus, because we differentiate with respect to upper limit, minus t ek t, that's all. So it is equal just integral from t to pi ek s ds. And finally, let us take second derivative. I need all these expressions, so let me put it there. Second derivative, lambda k ek 2 prime t will be equal minus ek t. So what we have? We have usual expression, usual differential equation for sine or cosine, yes. But also we have boundary conditions. Yeah, one is the following. See this representation. Put here t equal to 0. What you will have? You will have 0, 0. So ek is 0. is equal to 0. This is instead of this relation. Ek of 0 is equal to 0. And from this relation, we have that Ek prime of 0 of pi is equal to 0. Okay, so we have this equation, these two conditions, and now we are able to find all Ek's. And they became to be like sign. Let us do it. I think that it will be a good exercise for you for the next lecture. We will begin next lecture from the solution to this equation and from the series representation for Wiener process based on the Karunen law of representation for any Gaussian random element which we obtained today. This is end of our lecture for today. Thank you for your attention. Maybe somebody have questions or comments, please.
Well, I have a question. So actually, we can take any orthonormal basis in L2 which we want, and we still can get Wiener process.
Yes.
So the aim is to find lambda k's.
Yes, we can proceed as you said. We can proceed as you said.
Yes, orthonormal basis with continuous functions, yeah, as elements.
But be careful because you will need some extra operator. You will need embedding operator of this orthonormal basis into our space. So your representation will be like follows. It will be the sum. Here will be some vector psi. Here is your fk, and here is E of fk, where E multiply on E star are equal to Q. But of course, when E is not self-adjoint, we have a lot of difference. Yeah? This is the difference. You see?
Not really, but probably probably next week.
Surely we can proceed as follows, but this since is more complicated and related, I think, to special structure of Gaussian random noise, white noise, which can be related to our Gaussian random elements and related to the space of admissible shifts of Gaussian measure in infinite dimensional Hilbert space. And let me do some advertising. Next semester, the same course as this one will be done by Gaussian. Devoted exactly to this representation from some simple arguments and use a eigenbasis related to covariance matrix. Of course, you are right, and we can proceed as follows. Even you can check that this representation is valid. Just take finite sum. Yeah, it's easy to understand that it is true, but now we get the special subcase of this representation related to the case when E is equal square root of Q. Yeah? This is the difference. Yeah, and it is related to the very simple statement from the finite dimensional case. When you have standard Gaussian vector, and you need to get the vector with this one, then you can rotate this Gaussian standard vector as you need.
Yes.
So you can take any orthonormal basis. By
Yes.
rotation,
Yes.
by the backward rotation, it can be turned into our eigenbasis. So
Yes.
this reflects the appearance of this operator here. You see?
What kind of operator it is? It is the mean, or what is it? This I embedding.
This is in our case we use this one, but of course
Okay.
you can use, for example, any such operator. Take any unitary operator, any isometry in Hilbert space, rotate this, and you get the same. Yeah. So of course it will be the same distribution, but you have to pay. When you will back to the case of representation of inner process, you will need this embedding. Yeah. So it is interesting to find the representation based exactly on such argument. And for me, it was interesting also to put your attention that how we find it. We just use the following Sturm-Liouville problem. Yeah?
And how did you get these boundary conditions? I lost a little bit.
One of it is written there because when you put t equal to pi, this integral disappears, but this will be k prime in the point.
Okay, yes, okay.
Yes, and
Yes, so this is the second condition. Yes.
Yes, and the same for this one. Yeah.
Okay. Okay.
So
thank you.
It looks like it is natural, and also it reflects very deep connection. For people who know stochastic calculus already, it is of course evident, but it is very deep connection between the Brownian motion and second derivative, or with Laplace in finite dimensional case. Yeah. This is all things are connected, so it was interesting to relate it in this case too. By the way, it is good exercise just to find this eigenfunction and to write precisely the representation for linear process. Okay, thank you. This is the end of our election. Hope next time we will do everything in time.
Thank you. Okay. See you next week.
Bye.
Bye.